Okay, morning and welcome back to the second lecture. So yesterday we had lots of questions and I wasn't really able to cover what I wanted to. So I'll try to go a little fast today in the first half. So, at least for the first half, you'll see there'll be a clear transition. We can pause there and ask questions, but don't hesitate to ask questions anyway, even in between. The first part of today's lecture is what I hope to finish yesterday. It's again sort of finishing the complete story of what goes on when you actually try to do these experiments. So it's a very quick and simple introduction of the various facets of the experiment. So you will see what one has to do as an experimentalist to get these going. And then in the second half, I will discuss different kinds of qubits in some more detail and give you a little bit of a historical perspective of how these qubits evolved. Okay, so very quickly, yesterday, we just introduced the basic concepts of two-level systems, talked about superposition versus entanglement, a generic model of a quantum computer, and then I introduced the simplest superconducting qubit, which is a nonlinear oscillator, and I talked about how to control the state of that qubit by doing this Rabi oscillation experiment by driving it with a microwave frequency resonant with the 0 and 1 transition levels, and I mentioned how you can control exactly how to place the superposition on this Bloch sphere by just controlling the properties of this microwave pulse. So all of this, as you see, requires you to create microwave pulses of specific characteristics. So how does one actually do that in principle? And that's where we will start today. Okay. So the general problem you're trying to solve here is to create a microwave frequency pulse with varying amplitude and phase. There is nothing quantum mechanical about it. It's purely classical engineering problem. Okay, I can write this as in this general way as A of t into some sine omega t plus phi of t. So here omega is going to be at microwave frequencies like between 4 and 8 gigahertz typically, what we talked about. And we have to achieve, we have to create an ability to do this using some instruments. And a convenient way to do that is to break this up into two components, basically expand the sign, and then you have a term which is proportional to sine omega t and a term which is proportional to cos omega t. These are often referred to as the quadratures of the microwave signal. And then you see that the amplitude and the phase part sort of combine in this a cos phi and a sine phi term. And these are often referred to as the in phase and quadrature phase amplitudes. So if you can now create a signal whose sine component is modulated, amplitude modulated in a specific way, and the cosine component is amplitude modulated in a different specific way, then you can generate any such function. Yes. Yeah. Typically, it's assumed because if you have to really go back and think about AM modulation and FM modulation, typically the modulating signal frequencies are lower than what are referred to as the carrier frequencies. But this formula, of course, actually works for any frequency. You could have very high frequencies here, but then it's sort of difficult to visualize what we are doing. What we are thinking about here is that I have a high frequency signal at omega, and I'm slowly varying its amplitude and phase. Slow here, could be 10 times slower, 100 times slower, or maybe even similar speeds. But typically, that's the sort of regime one works in. So this now gives you a generic way of doing that. And there are instruments which allow you to do such an operation. Okay. So in order to generate these sine omega t terms, we use a microwave generator. As I was mentioning yesterday, these are very easily and very commonly available. With improved technology, they become very, very cheap. You can get a USB powered one for like $1,000 or so. But these are highly stable and highly pure microwave sources. You can get a line width of these CW tones, down to a hertz or even less than that. So you create this using a microwave generator. I have shown one particular example here. There are many ways to do that. And then for creating I of t and q of t, you use something called an arbitrary waveform generator. Right? So here you need a little bit more flexibility because these are, in principle, can be different shapes depending on exactly what you're trying to do. So an arbitrary waveform generator is basically a digital way of creating the signals. You define your waveform shape in the digital domain. And then using digital to analog converters, such instruments are able to generate these analog signals based on the digital input. So the moment you are in the digital domain, you have complete freedom. You're only limited by the sampling rate of the system, but how precisely you can define the waveform, but it becomes very, very easy after that. Right? So you now have the I, Q, and the sine components, and then you need a device called a mixer. This is again a nonlinear device typically constructed using diodes. Again, a classical device operating at room temperature. And it has 4 ports, as you can see here. This port here, which is labeled L, is the one where you feed the sine omega t term in. This is also called the LO or the local oscillator. And then you feed the I and Q into the I and Q inputs of that. And from the R output, you get exactly this operation. So the mixer multiplies a high frequency signal with a low frequency signal. And a specific type of mixer like this one, which is called an IQ mixer, multiplies the component you are sending in and a 90-degree phase shifted component as well. So that if you send in sine, you also get cos. Okay, so that happens internally. You don't have to send sine and cos separately. It creates the cos internally by just phase shifting. So once you're able to do that, you can create this kind of a pulse. And the exact same principle, yes.
This mixer seems to be like an analog device. So it's just some circuit inside that does this multiplication.
Yes.
And then sine and cos, they could in principle have different frequencies. Do you need different mixers to different frequencies? To what degree a mixer adapts to different carrier frequencies, because you have different qubits?
Right. So typically these mixers are designed for a range of frequencies, which could be very large. For example, a typical mixer like this could work all the way from 4 to 20 gigahertz for the LO, and could work all the way from DC to 4 or 5 gigahertz on the I and Q channel. So those are model dependent, how much price you're willing to pay for that, and how much accuracy you want in this operation. So this is the ideal thing you actually want. In reality, it doesn't do exactly this. I'm not going to go into that today at all. But just to give a quick hint, it turns out that it's not able to keep sine and cos exactly, so their phase is not exactly 90-degree different. When I becomes 0 and Q becomes 0, ideally you want the output to be 0. That doesn't happen. There's always a little bit of signal bleeding through. So you have to do various calibrations to make it work as close as possible to this. Yeah. These are very old technology. It's been around from World War II days, I guess, for use for radars and other things. Okay, now the same process can also be applied in reverse. So this we typically refer as modulation or up conversion, where you're taking a low frequency signal and up converting into a high frequency signal. But you can do the same thing in reverse, where now you send your reference tone as always, but now the input signal comes into the R, and then I and Q give you the demodulated output. So if the same thing was sent to another mixer, the whole process will happen in reverse, and you can recover I and T. Why am I mentioning that? Because this is exactly what happens in the measurement process. Remember, the measurement also is a high frequency signal whose phase I'm trying to detect. And this is exactly, I want to know what the I and Q values are to extract the phase of that signal. So we do this in reverse at the end of the cycle as well. Okay. Now, this was pretty much the methods that were used till very recently. In the last few years, there's a completely new sort of technology which has emerged. Part of it is not surprising. In principle, you could have a digital to analog converter which works at 5 gigahertz, right? But typically that means that it has to sample much faster than 5 gigahertz. So they tend to become very expensive. So those machines do exist. You can have DACs which sample at 100 gigahertz or so, very expensive. But recently, primarily driven by 5G mobile technology, there are this is a board from Xilinx, which uses a technique called multi-Nyquist zone. Now, I'll just spend 1 minute to mention that because I always find it fascinating. Most of you who have learned about digital to analog and analog to digital, we learned this thing called the Nyquist criteria. which says that if you want to digitize a signal of frequency f, you have to sample it at least at twice that frequency, right? The simple picture being you have a sine wave, you at least need 2 points per sine wave to sort of at least have some resemblance to the original waveform. Turns out that this is not the strict definition of Nyquist criteria. What you actually need is that your sampling frequency should be twice the bandwidth of the signal you are requiring, which means that if you have only a 1 megahertz bandwidth signal at 10 gigahertz, you can actually get away by only sampling it at 1 gigahertz. Sounds very strange, but essentially, this, if you are interested in this idea, come talk to me afterwards. But it essentially uses the nonlinearity of these processes to look at images of the signals, and you can create high frequency signals even though your digitizer or your DAC is actually updating very slowly by choosing appropriate filters. And this has brought down the cost of these DACs very low. And again, the reason is that 5G cell phones use frequencies in this range, in exactly the same range. And mobile communication is almost identical to the qubit experiment. The only difference is that the I and Q signals are your speech and your data, and it has to be modulated onto a carrier, transmitted, and then recovered back. So you needed a cheap and efficient way of doing this, and this is the result. So again, we have benefited from this. There can be a factor of 10 to 20 in the cost of generating lots of such signals as you scale up to the qubits. There are now open source projects which give you free source code, and you can buy this board from Xilinx as an evaluation module for very low price. And you can use those codes or write your own codes. But there are also now commercial products which are based on this technology already in the market. Okay, so this is, I feel, is going to play a big role in at least superconducting qubit control. It gets rid of all the problems I was mentioning with the mixer. None of that is now relevant. Everything is in digital domain, and it directly up converts to the frequencies you need. And it does the same operation in reverse as well. You can digitize now a 10 gigahertz signal by sampling only at a gigahertz or so. All right, so don't worry about the circuit. The idea was just to give a sense for how many components typically end up getting needed for doing a qubit experiment. This is a setup for 3 qubits. So you can see there are 3 sources here at 3 different frequencies. There are 3 mixers for the modulation. The arbitrary waveform generators are sending the I and Q pulses. And then there's a 4th mixer for doing the measurement pulse as well, because that is also created in exactly the same way. All of these signals are now combined, and then they go into the device. And then the signal which comes back from the device again goes to the mixer now in the demodulation operation. And then it goes into a PC with a, basically an analog to digital converter. The idea is only to give you a sense of the complexity which typically goes in when you're even doing a few qubit experiment. So this is now all the control electronics. Then you need to go into the cryogenic environment. Here is the picture of a typical dilution refrigerator, which cools down to about 10 millikelvin. I'm sure most of you have seen these images. There are these various plates, each one successively lower temperature. And then this bottommost plate here is the one where you attach all your experiments. So all your things are screwed onto this plate, and it cools to this temperature. Now, in order to be able to do the experiments, you have to bring signals down all the way from this setup you had at room temperature down the fridge into this 10 millikelvin stage. So that requires a lot of coaxial cables which guide these signals down. You have to make specialized filters. I will elaborate on that a little bit. Of course, you need your devices of different types. You also need to use shielding to protect these devices from magnetic fields and other kinds of radiation which is coming from the outside. So you put all of this together, and then you cool your fridge down, and you can start your experiments, right? So now I'm showing you the typical wiring of the cryogenic part inside the fridge, what goes on, okay? And there are many components here just for a single qubit. This is a typical setup for 1 qubit measurements, okay? I'll walk you through this in just the next couple of minutes. First, you have these coaxial cables. These are the ones I showed you, but you can barely see these cables which are like coming from here. These cannot be any cables. Remember that you're starting from room temperature, and these are made out of metal. If you put a nice conducting metal like copper, you'll never cool down. because you're going to thermally short all of these different stages. So you have to use special cables which are thermally isolating. But because of Wiedemann-Franz law, they tend to be poor conductors of electricity as well, if they're poor conductors of heat. So the price you pay is that the signals will get attenuated. Typically, one uses stainless steel as the material for this coaxial cable, but there are other combinations which we can use which provide trade-off between thermal conductivity and electrical conductivity. But this attenuation is actually, or the loss of the signal as it comes down, is actually not really a problem on the way in. In fact, we need to put attenuators specifically. These are these yellow colored things shown here with various values of attenuation. Why is that? Earlier, we were worrying about the heat reaching the low temperature. Now we are worrying about the fact that there is thermal electrical noise at room temperature, which should not make its way down to your device. If you had a straight path with no attenuation, you're never going to do the experiments. Remember, I made a big deal about cooling down to 10 millikelvin to suppress all thermal fluctuations. This is exactly the same thing, except it's coming in form of electrical Nyquist noise, or Johnson's noise, if you want to call it. So we have to put sufficient attenuation and we distribute it at different temperature so that by the time that signal reaches your device, it doesn't have any noise or insignificant noise coming from the higher temperature stages, just because they're hot. So these attenuators are added in addition to the attenuation the line itself provides because of what you have actually used. Then typically you have some filters. Reflective filters are typically made out of inductors and capacitors, so they don't work on absorption. They work on reflecting the signals out of band, which you typically need. And that you typically put in various stages because there can again be noise from outside the band of your interest coming down and causing problems. You also need something called infrared blocking filters. I believe that this idea was aware many years ago, but sort of got lost, and then it was rediscovered maybe 10, 15 years ago when people started paying attention to this. This again is a very surprising fact. It's just because that you are inside a cryogenic environment where there are also hotter parts of the fridge. So you see there is 4 Kelvin, there is 0.7 Kelvin. These radiate black body radiation corresponding to that temperature. Now you might say that, okay, that's very low temperature, how does it matter? Turns out that at the microwave frequencies where photons are high enough energy to break superconductivity, that is break Cooper pairs. So if the energy is larger than the gap of aluminum, there is enough photons available, enough density of photons available to actually destroy superconductivity in your devices. And that can come directly from the hot parts of the fridge radiating through free space, like the vacuum inside the dilution fridge. So that's why we put our devices inside radiation shields, like boxes inside boxes. But they can actually also just come screaming down these coaxial lines, which are actually not designed for these 100 gigahertz frequencies. At those frequencies, it just looks like a tube, forms like a nice waveguide, and these photons come screaming down. So now we put some additional filters in line of these coaxial lines, which basically is some absorptive material which absorbs very high frequency radiation, so that these very high frequency photons also don't reach your device and break Cooper pairs. The thing was that in the early days of the experiment, the coherence time of these devices was so poor that these small effects due to these other things were never felt. And then as we fixed the problems in the devices, we started getting restricted by other things. And then we said, oh, okay, we have to do this now. You also need devices called circulators and isolators. These are these red boxes showing these arrows. They actually allow signals to propagate only in the direction shown. So which means that if a signal comes from port 1, it will actually go to port 2 and not to port 3. And similarly, so it sort of gives you a directionality to the signal. These are needed in order to do two things. One is to separate incoming wave from the reflected wave. So remember, we have to measure the scattered wave from the device. And they also help in protecting the noise coming from the wrong direction. So if there is some noise coming down this line, so this is actually the output line, so you expect signals to go up this way. But these amplifiers here can actually radiate noise, and there could be other kinds of noise also. But you see that this signal here can have this device here will actually prevent signals from propagating down in this direction. I'm just noticing that this arrow might be in the wrong direction. But anyway, and then you need cryogenic amplifiers. So here is one cryogenic amplifier, which is typically operating at 4 Kelvin. These are commercial high electron mobility amplifiers, which keep the noise low. But also, we use our own superconducting circuit-based amplifier called parametric amplifiers, or param. These are highly critical for those very nice measurements I showed you in yesterday's lecture, because these are, in some sense, the world's best microwave frequency amplifiers. They add the minimum amount of noise quantum mechanics says that you have to whenever you amplify signal. So they form the first stage of the amplification. So the qubit is somewhere over here, which is called device. The signal comes down here, and then the measurement signal is routed back through this amplifier, and it again amplifies in reflection. So the scattered wave is actually an amplified copy, and then it goes up here, gets further amplified, and then there is more processing here till it goes to the demodulation circuit at the outset. So I really want to sort of presented this to give you a sense of the complexity of these experiments in terms of the various aspects you have to take care of in order to get it to work. And this is the setup for 1 qubit. So imagine doing this for hundreds or thousands or millions of qubits. It is a formidable challenge. And there are people who are working on solving many of these things. It may be possible to compactify, simplify, and miniaturize many of these things, but it is something people have to work out. These are not fundamental limitations, but these are technological challenges we have to solve as we go ahead. Okay. And then you also need sometimes magnetic flux lines to tune, to apply those small magnetic flux to tune the properties of your devices. And they typically are low frequency lines coming down the fridge as well. Okay. So again, just to belabor that point again, this is now the amount of components and setup for a 4 qubit experiment. It's just 4 copies of the same thing. And you can see how many, there are already some 50 to 100 components here, which you have to choose the right one, make sure everything is well thermalized and all of this. So once you have everything ready, one of the first experiments you do, you need to know what your qubit transition frequency is. Right? You design it, you sort of have an idea what it should be, but you never know it very precisely till you actually do the measure. So the way that works is that you have your qubit coupled to your cavity. Here, this example is shown where the qubit is actually this black chip in the middle, and the cavity is really a physical cavity which forms the harmonic oscillator. So here it's just a piece of copper with a hole, where the size of the hole determines the resonant frequency. So this is sort of like your atomic cavity QED type of experiments, and you put your qubit chip in the middle so that it interacts with the photons inside, and then you use these connectors here to send the signals in and out of the cavity. There are other ways of doing it. I showed you some pictures yesterday. Then what you do is that you send a fixed frequency microwave tone at the measurement cavity frequency, because you're trying to look at the phase shift of the measurement cavity frequency signal. Then you sweep, you vary the frequency of another tone, which is close to the expected value you are imagining. And then you look at the response of the phase as a function of this frequency. So for this particular 3 qubit device, it may look something like this. So this signal is phase as a function of frequencies. I've broken it, the axis up, because these frequencies are quite far from each other. And you see some features over here. Okay. Let's focus on these broader features. These broader features are actually the 0-1 transition frequency of the 3 qubits which were in this experiment. So this is 0-1A, this is 0-1B, and this is 0-1C. This is actually the first way you identify that, okay, are these frequencies in the right place? So that, because remember that you have to apply the pulses at exactly these frequencies to do any manipulation. What are these other sharp peaks over here? Okay. This first one is the broad one, is the 0-1. These sharp ones turn out to be 2 photon transitions from 0 to 2. So they are actually at half the frequency of this difference. which is why they are close to omega 0, 1, because this is a nearly harmonic ladder. Remember, it's only weakly unharmonic. And this is also important, and this is done by increasing this qubit tone power slightly so that this 2-photon transition now becomes highly likely to happen. The matrix elements of the system doesn't allow a direct single photon transition from 0 to 2. It's basically a harmonic oscillator type of situation. Only nearest neighbors are coupled in terms of finite matrix. So it's a higher order process, but then you get this, and with these two numbers, you now know the first 3 levels. Okay. And for the transmon, that is sort of the most important. It tells you that your frequency is in the right place and the nonlinearity is in the right place as well. Because from now, you know that how far away the second level is. So this is the first step for doing qubit measurements. Yes? No, it's just, again, a 2-photon Rabi oscillation from 0 to 1. What's happening in this experiment is that you're sending a continuous tone and sweeping. So when it becomes into resonance, part of that population shifts to the higher level, and then that basically results in a part of the phase shift coming down. The coherent experiments, which are like pulse experiments, start next. So you do now the Rabi oscillation experiment. Yes. Why is this sharper? Because this is a higher order process. It essentially, for the particular power you're choosing, the resonant condition happens over a narrower range. These widths of these is also not really representative of the, I would say, the quality of the transition, because here the measurement is also present at the same time, and you also have power broadening. When you drive this Rabi oscillation, this transition with a strong tone, you actually broaden the transition. So they don't actually represent the true, if you want to say the spectral line width. You know, when we talk about atomic spectra, we have this line width, which we say is basically a representation of the dissipation which is present in the environment. Here, this is close to it, but it's not exactly, because it's affected by 2 other things. One, measurement is causing a broadening because the measurement is always on. And also, you're driving the system with much higher power. Just because this is the first experiment, you want to know where the frequency is. So we actually do further experiments to resolve this down to few tens of kilohertz or even better. Right now, this is much broader than it needs to be. But at the same power, this transition is sharper because it's a higher order process and it becomes resonant only in a narrower range of frequencies. That was the question.
So just looking at the plot, how do you know which frequency is which?
Okay. That's because we have designed the qubits in a particular way. And so, these frequencies are roughly 1 gigahertz apart. So your estimate is definitely accurate to that level. And for this particular 3-qubit device, we knew that there will be 3 lines. So once we know which is the lowest line and what is the middle line, which is the largest one, we know which qubits we are talking about.
And also the side peaks, like the sharper ones.
Yeah, so the sharper ones are always associated with this. So you see this difference here is about 100 megahertz or so. So we know that the sharp peak, this sharp peak is associated with this one. And the way to check also is that if you lower the power of the qubit tone a little bit, these sharp peaks disappear. That's how we know that that is the anharmonicity peak and not the main.
Thank you.
So then you start to do the coherent experiments where you drive the qubit on resonance. And as I said yesterday, you get these coherent oscillations, Rabi oscillations. But now you have to use this to fine tune the length of your pulse. For example, if you want to take the system exactly to the excited state, essentially you need to go to the top here. So this is the length. This is just the zoom in version of that. This point is called the pi pulse because it takes 180 degrees on the Bloch sphere. Okay? And the point which is halfway is called the pi by 2 pulse. And this is the pulse which allows you to create superpositions from 0 or 1. These are the typical 2 pulses you need to calibrate in order to start doing any kind of sequence of gate operations. Right? Now, this is really the first step, and I'm not going to go into the details. You actually do further fine tune because the resolution in these measurements doesn't allow you to very precisely tune that time. You actually do other protocols by, for example, by sending many of these 180 rotations together and seeing whether the state ends up where you are, and then you fine tune them till you very precisely get that. And that's actually how you ensure that your microwave pulses are precisely implementing the unitary operations you intend to do on that thing. So this whole process of calibration which goes on in order to achieve this and get the precision you want. Once you have this, the next basic property you characterize is the decoherence processes in this system. Okay. One of the first measurements you can do is measure the relaxation time. You now have the pi pulse, so you send the pi pulse, then you wait for a certain amount of time, and then you send your measurement pulse and record the phase. And then you repeat this about a few thousand times and create an average. Right? This is now giving you an ensemble average. And then that average is repeated for different waiting times, delta tau here. And this is the result you get. So again, this is plotting the probability of being in the excited state. So I've taken the phase value corresponding to the excited state and normalized that value to 1. And then you see that at very small time delays, the probability of being in the excited state is 1, because you made the excited state. But as this time delay increases, you see that that probability slowly decays and approaches 0 in an exponential fashion. This is essentially measuring the relaxation, because as you wait longer and longer, the chances that you will actually measure the excited state here decreases. And that happens typically in an exponential fashion for these things. Okay? So this is the ensemble measurement that gives you the T1, and essentially is measuring the relaxation process. But just to remind you, yesterday I showed you this plot, which was the real-time version of the same type of measurement, right? Where I was watching these individual events every time it was decaying. And if I actually take the statistics of this and average all of them, that would again recover an exponential. But there could be some differences in the time constants, because here the measurement and the free evolution are separated from each other. Whereas here, the measurement is on all the time. So you can actually have quantum Zeno type of effects where the measurement might affect the dynamics of the qubit itself while it's decaying. I'm just throwing that word as a teaser. We can talk about that later. Yeah. So is there also a T2? Yes, that's coming next. Yeah. So from this, you get your T1, you fit this exponential, and the time constant is what you find as T1. Typical superconducting qubits are in the 50 to 100 microsecond range for T1 these days. Significant improvement from 20 plus years ago when superconducting qubits first started. Okay. Then you come to look at the dephasing part, or the T2 part, which Ganpathy was mentioning. So this experiment is slightly complicated, but I want to walk you through it because it's important to know how these experiments are done. So the sequence consists of 2 pi/2 pulses, which are separated by a certain time, delta tau, and followed by the measurement. An added complication is that these pi/2 pulses are typically not sent at exactly the resonant frequency of the qubit. So it turns out that even if you're slightly off resonant, you can actually do these operations, and we calibrate them exactly the same way. And the reason for this slight detuning is there was this question yesterday about the free Larmor precision. Now, the qubits reference frame and your measurement tones reference frame, which actually sets this synchronization between the lab frame and the rotating frame, is now slightly detuned. Right? And in reality, it's detuned by a fixed amount. So what's going to happen here is that now if I look at the block sphere picture, I start at the ground state and I do a pi/2 pulse, I come on the equator. But now I'm in a reference frame which is detuned from the qubits Larmor frequency. So this vector now starts to precess at a fixed rate around the equator, exactly at the detuning frequency. And in fact, remember I was telling you that you do more precise measurements. This is one way to know exactly what the qubit frequency is, because those oscillations are reflected in this measurement. And this you can fit very precisely what frequency is, and you know your measurement tone, the drive tone very precisely up to a hertz. So you subtract the two and you get your exact qubit frequency. Okay. But why does it oscillate like this? Because the second pi/2 pulse remember that these things always rotate in the same direction if the phase is chosen in the same way. So you put your pi/2 here, and if the second pi/2 happens immediately, that means delta tau equal to 0, you will come to the ground, to the excited state. Okay, so that's the first point over here, where it starts at the excited state with a probability of 1 of being in the excited state. That makes sense. 2 pi/2 pulses make a pi pulse. The moment you delay it a little bit, now this vector is starting to precess. If you precessed exactly all the way, say 180 degrees, so I was here and now I'm here, and when I rotate, it's still going to rotate in the same direction. So remember, I was here, I rotated like this. Now I have rotated along the equator and come on the other side. And that pulse is going to rotate in the same direction, which means this went to 1, but that now goes back to 0. So if you wait a time which is exactly half the period, you will come back to the ground state. And for all other values in between, you will end up in some other superposition, which varies continuously sinusoidally. And that's why you get sinusoidal oscillations. When you do this experiment with a detuned pulse, you can actually do this without detuning, and then you just, you should ideally get 1, 1, 1, 1, 1. So it doesn't matter. Again, if there was no decoherence, this would be a perfect oscillation from 1 to 0, back to 1, and so on and so forth, and it will go on forever. But because now there is decoherence, both relaxation and dephasing, this exact synchronization doesn't happen, and you slowly see the amplitude of the sinusoidal oscillations decaying. So how does dephasing affect it? Because remember that this entire thing is reliant on knowing exactly the precession rate so that it oscillates at a precise frequency. But this slow frequency fluctuations, which I was talking about, now the qubits Larmor frequency itself is fluctuating in time, which means that your reference frame, with respect to the reference frame, your detuning is fluctuating slowly. And that gives rise to not knowing exactly where the vector is as time goes on. So that's the reason for these decaying oscillations. But also, if there are decay events which takes the system to the ground state, you have the same kind of effect. And you fit an exponentially decaying sinusoidal function. The frequency of that sinusoidal function tells you the precise detuning of your qubit from your drive frequency. That's how you know your qubit frequency very precisely. And the exponential decay constant gives you the T2. And the expression for the T2 you get is actually a combination of the decay time due to the relaxation and due to pure dephasing. I don't have a slide for that, but there is also something called an echo experiment, which people in NMR are familiar. And what you do that is in between this sequence, right in the middle, you put a pi pulse. And that just flips the direction. So you went down, and then if you put a pi pulse, you're going to come up here, and then you do a pi/2, you're back over here, right? Similarly, if you're halfway around here, if you do a pi pulse, it sort of flips this. The way to think about it is that if your detuning is slow, then that precession actually, the flipping of the Bloch sphere to the other side causes whatever phase you accumulated to cancel again. So if you do an echo experiment, even when you're detuned, you actually don't get any oscillation because whatever you accumulated in half the period from here to the middle gets canceled in the other half because you have flipped the state to the other side. But apart from that, it also gets rid of the lowest frequency fluctuations of the qubit. Because if the noise within this time window is constant or not varying much, then the noise also is going to push you in a very deterministic way a certain amount. And on the other half, it will push you back exactly the same amount. Zoom. Yeah, so normally when you do any rotations, you always drive it exactly at the qubit frequency. For this experiment, you drive it slightly off, maybe like a megahertz or 2 megahertz, not too far away. And that essentially changes the reference frame in which you're working. That's all. So now your qubits is going to process with a frequency not equal to the Larmor frequency, but equal to the difference of the Larmor frequency and your drive frequency. Yeah. Oh, that because you can check by changing. If you have no idea of where your qubit is, which is not possible because you chose the drive frequency to be detuned. So it's really the difference of, let's say I from the spectroscopy, I got my qubit frequency to be 5.1 gigahertz. But I don't know the rest of the decimal places. Now I will choose the drive frequency as 5.101 gigahertz, which is expected to be 1 megahertz detuned from what I thought the qubit was. Then I expect this oscillation to be 1 megahertz precisely, but I will measure this oscillation to be 1.142 megahertz. So I get those extra digits, right? Because I know my drive frequency very precisely, and I can fit this oscillation very precisely. Now I know my qubit frequency very precisely. So that's okay. So the echo experiment allows you to get rid of the lowest frequency part of the noise in your qubits frequency fluctuation. And it's often used as a standard protocol in many sequences to sort of undo this effect. But if the frequency is varying much faster than this time scale, then that cannot be removed out. So in the ideal world, in some experiments where the dephasing is dominated typically by some kind of a 1 over F noise, which is highest at low frequency and then dies down at high frequency, when you do the echo experiment, you get that the T2 echo is exactly 2 times T1. So if your T1 was 50 microseconds, your echo time would be 100 microseconds. So that tells you that you are dominated by low frequency noise. If you don't see any change, then you know that there's a lot of high frequency noise. And this gives information on how to adjust your setup to look for problems, why it is high frequency, why is it low frequency, and so on. Okay. So once you all have all of that, at the end, the quantum algorithm is just a sequence of operation. And those gates, quantum gates, single qubit or 2 qubit gates, is just a microwave pulse with specific characteristic. Each such microwave pulse has to be calibrated. You have to know the exact shape and the length and everything. You have to do it precisely so that you know it's doing the operation you intend. And these calibrations often have to be repeated periodically in time because your electronics drifts, you no longer have the same pulse, so you have to do these calibrations over and over again. And then finally, the coherence time determines how many such gates can be executed. So this x-axis here is like basically your time axis. If you do too many gates, then there's a probability of having a random event due to your decoherence processes increases, then you can no longer trust the results of your measurements at all. So that was this discussion about circuit depth yesterday. So depending on the coherence time, depending on how good your gates are, that sort of determines what is the useful time you have to do any operations.
So in a very naive way, can we think that the first gates are more accurate than the gates that are applied later because the qubit is getting more and more mixed by time? So
I wouldn't put it exactly like that. The gates are still accurate in the sense that they are carrying out the rotation they are supposed to. It's just that the qubit state is not where it's supposed to as time goes on and it accumulates.
Yes. Can you play the following dirty game? And I mean dirty. Introduce noise, introduce the dephasing in a controlled way, and then you can test different engineered reservoirs like different power loss, white noise, and so on, and see how the effect goes.
Absolutely. People have done these experiments. I've also done some experiments earlier where we put in a noise bath and then see how that affects. You can do all of those things. So these noise baths can be introduced again using some arbitrary waveform generator to create the noise spectrum. They can come from your measurement lines, the drive lines. They can also come from the flux lines. Because for example, if you have a tunable qubit, like with a SQUID, then you can introduce frequency fluctuations through that line. And in fact, putting a flux line often is a problem because it can bring in noise from that channel. So you have to do it carefully. But absolutely, these experiments have been done. Are there any other questions on this part? So now we'll then move on to talking about the qubit design itself and sort of a historical evolution. Yeah.
So can you do this real-time measurement for the T2 also?
No. So the T2 is sort of by definition an ensemble measurements. You can, in the sense that, for example, you could choose one point, and people have done these experiments where they, for example, will choose a point, a time difference, which brings you exactly to 50-50 probability. And then any small deviation will give you a big signal. So you can now monitor the changes in frequency of the qubit much faster as a function of time, because this curve could take minutes to average and give you. And if you want to look at how the qubit frequency is fluctuating in time, then you can't do that. But you can sit at one point, and if you have a very high fidelity measurement, you can get some information. But it's a trade-off, right? It's basically the trade-off of, do you integrate long enough to increase the signal to noise ratio, or you keep the time window small so that you have more resolution in your measurements? But these things have been done, for example, to look at how quasi-particles, which often are created due to, for example, these high frequency radiation processes, and they, if your qubit is sensitive to charge, its frequency will fluctuate. And if you have a fast measurement of the frequency versus time, you can actually see these hops. So you see a quasi-particle will jump in, and that changes the charge by 1 electron, and the frequency will jump, and that will give you a signal. And you can actually look at that spectrum, and people have done experiments on this to understand these quasi-particle dynamics in these things. Is Serge here? There. I mean, do you want to add anything to that? I mean, for these kind of experiments? Yeah. So let me.
Very often the
takes 3 seconds before it turns on.
Yeah. Very often the T2, the dephasing comes because there is noise in a nearby system. So you can also monitor the state changes in the nearby system, which tells you about the T2.
Oh yeah, this was done somewhat recently where they inferred this low frequency noise by measuring a neighboring system and tried to sort of correct for it. So there are all kinds of things. Anything else? All right, so let's move on. So before we discuss superconducting qubits, yesterday there was this question about what the Josephson junction is. So I'll just give the basic equations here. So Josephson junction is a superconductor insulator superconductor sandwich. The tunnel junction, the electrons or Cooper pairs in this case tunnel from one superconductor to the other through the thin insulating barrier. The symbol for that electrical symbol is a cross. Sometimes you see a cross with a box, which I believe means it accounts for the capacitance of this structure. Remember, it looks like a parallel plate capacitor, right? Metal, insulator, metal. So there is a capacitance here. It's called the Josephson capacitance. So the box symbol is supposed to capture that it's inductance plus capacitance. Brian Josephson wrote down the electrical relations between this device, and these are these two relationships. This one says that the current through this circuit, so through this device, is equal to a proportional constant I naught into sine of delta. Now this delta is often referred to as the gauge invariant phase difference. If you just want to think in electrical terms, it's sort of like the flux across an inductor. And you can see that from the second Josephson relationship, that you have that the voltage across the junction is proportional to the first time derivative of this quantity called delta, right? So we know from Faraday's law that V is d phi dt. So it sort of has, it's a dimensionless thing, but after multiplying by the flux quantum, magnetic flux quantum, it sort of has units of flux. And in fact, the correct way you will see in literature is that the definition of delta actually comes from the inversion of this equation. So you say that delta is the time integral of the voltage from 0 to t across this device. what does this equation signify? If I is less than I naught and fixed, then delta, there's a solution for this equation. Delta is a constant, which means delta dot is 0. So no voltage. That is the superconducting state of the Josephson junction, provided this current is smaller than I naught, which is often called the critical current of the junction. So if I is smaller than I naught and not changing, then you have 0 voltage. There's no voltage across it. It looks like a superconductor with no dissipation. But the moment you go to an AC signal, if I is a time varying quantity, then delta is also a time varying quantity and voltage is also a time varying quantity. But because one is the derivative of the other, you get sort of a 90-degree phase shift, and current and voltages are not in phase, which is why this is not going to dissipate any energy, even for AC frequencies, even though there is a finite voltage now developing, as long as current is smaller than I naught. And this is the regime in which all superconducting qubits work. I is much less than I naught typically. You don't go beyond that. There are other experiments and applications where one goes beyond I naught, and then you enter what's called the normal state or the voltage state of the Josephson junction. I'm just throwing it out there because some of you might have heard about these terms. Okay? So when you now take these two terms and you try to connect with an electrical element whose properties might look similar to this, and basically you can do that by, sorry, maybe before that, I should just point out this picture here of the tunnel junction. So these are aluminum films, and the overlap region here is where the junction is formed. And the sine part here is what gives rise to the cosinusoidal potential we discussed yesterday, that's shown here. And again, for comparison, a parabolic potential is overlaid to sort of show that the quantized equally spaced levels of the parabola, for the cosine, each level is subsequently slightly smaller than the next level over there. That's what gives rise to the nonlinearity. When you actually use this in the equations of motion, you will see that this current looks like a force. And that's why the potential is a cosine. So sine, force is proportional to sine, potential is proportional to cosine. Okay. You then can combine this to create an effective inductance by using this fact that V is d phi dt or V is L di dt, right, from Faraday's law. And from that, you can write an expression for an effective inductance because the electrical property seems to resemble that of an inductance. And you get this. You can either have the inductance written in terms of a constant here, phi naught over 2 I naught. So this is magnetic flux quantum divided by 2 pi I naught. There's a constant here, which we often call as linear part of the Josephson inductance, Lj0, divided by cos delta. So it tells you that the inductance depend on the value of delta. You can also replace cos delta from this equation, and you can write the inductance now as a function of the current flowing through the inductor. So again, you see that I has to be less than I naught, otherwise this solution sort of blows up, doesn't have a solution. And as I approaches I naught, the inductance increases. Okay. Here, this I is really, you should really referring to a constant current. But this is sort of the origin of the nonlinearity. You can work with these in terms of equations of motion, or you can work with these in terms of an expansion of the inductance as a power series in current. So that's what gives rise to the nonlinearity. And then it's just an inductor, you put a capacitor, you get an LC oscillator, and you get your transmon qubit or other kinds of nonlinear oscillators you can build using these systems. Okay? So the important thing here, as again to mention, is that the only known sort of device which is nonlinear and non-dissipative by construction. In the ideal world, none of these processes can induce dissipation. And this is really critical for the fact that we have been able to use this in superconducting. This is not so common. Typically, nonlinear experiments in the past were done in optical systems. And there, A, the nonlinearity is hard to come by, which means that you have to put a lot of photons for the nonlinearity to manifest itself. And two, typically, those mediums will have lots of dissipation. So this is really a pure nonlinearity, which comes without dissipation if everything is done correctly and has played a major role in the whole field of microwave frequency quantum optics, which you can do with these experiments, with these devices. Okay, so now the superconducting qubit. So this is a picture from a review article from 2013. So
I have a
it's
question.
Slightly dated. Yeah.
I have a question. Here.
Yes.
Actually, in the previous slide,
Yeah.
actually, I remember you saying it to be a weak link to be an insulator, right?
What is?
Weak link, superconductor, two superconductors are there and separated by a weak link, that is the insulator.
Yes.
And so can we do all these kinds of thing instead of an insulator, but we have a ferromagnet as a weak link?
Yeah, there are ferromagnetic Josephson junctions.
And how it will differ from having a magnetic material instead of
So, well, it will respond to magnetic fields differently. It also affects this current phase relationship differently. I have not studied that too much, but this is a magnetic tunnel junctions are a very common and interesting area of research. A lot of people are working.
and delta is basically the phase difference between two superconductors, right?
Yes, so that is another definition that people often write, that if you define the wave function of the left-sided superconductor with a phase, the right side superconductor has a different phase, and it's that phase difference. But operationally, people use this definition in reverse to define it more strictly. This is actually like sort of comes from some very strict theory principles, which I don't understand very well. But there's all this gauge business has to be done properly. Yeah.
I mean, this question is out of curiosity. Let's imagine a situation where you do not have the phase difference between two superconductors, but still maybe due to some breaking up some symmetries, can we get such nonlinear Josephson junctions? For example, there is new thing called anomalous Josephson effect, where you do not have to necessarily apply any phase difference, but still you get a Josephson current.
But I'm not sure what you mean by apply a phase difference. I mean, this here is just parameterizing how currents and voltages are related to each other.
No.
Without phase, is the phase applying is not giving the nonlinearity. Right? The fact that the phase function is inside a sign is what's giving the nonlinearity. I'm not sure. So maybe let's discuss this offline. Okay. Yeah, so this is a map from 2013, slightly outdated. There are some new types of qubits, which actually I won't even have time to discuss. But it sort of emphasizes this idea that you have three building blocks: a capacitor, a Josephson junction, and a linear inductor, and that's it. But by combining them in different configurations and different values, you can create all kinds of Hamiltonians. And that's already gave rise to a zoo of different kinds of qubits. So this was at that time being referred to as the periodic table of artificial atoms. It's not discrete, it's a completely continuous space. The two axes are parameterized in terms of the Josephson inductance normalized by the linear inductance, and the capacitance, again, normalized by the Josephson junction with some factor. Essentially, it sort of gives you these 2 degrees of freedom you have with respect to each other. And these different qubits, which have been named with all these things, and we'll be discussing a few of these in the next half an hour or so, fall on different points on this. So for example, the transmon qubit does not have a linear inductor, right? So L is, if it is L is not there, it doesn't mean L equals 0, it means L equals infinite because it's in parallel. Okay? So L being infinite means that on this axis, it corresponds to the point 0, which is why it is lying somewhere around here. Okay? This axis is this. It's the capacitance divided by the Josephson inductance, and then this factor basically is again h bar over 2e squared. It's just a normalization factor to give the same units. So similarly, there are other qubits which have finite values of inductances. So one of the things we'll be discussing today is the fluxonium. But the first qubit which was invented was actually this thing called the Cooper pair box. And that also doesn't have any linear inductance. It's actually the same circuit as the transmon. Only difference is the parameters are different. So you see it falls on different points along this axis. So we will be looking at the Cooper pair box, the quantronium, and the transmon. and the fluxonium in the next few slides. Okay. So what is the Cooper pair box? It's a slightly funnily drawn version of this simple circuit.
So I have a question.
Yeah.
So the entire discussion is based on, so the sign delta dependence is based on 2E transfer between the two superconducting islands. So is the E transfer completely ruled out, assuming that you have complete superconductivity, or are there mechanisms which?
In the ideal model, yes,
Oh.
but you can include. So in many cases, you can have quasi-particle transport as well. That will introduce other terms and cause other processes. But you experimentally, you try everything to make sure that you're dominated only by Cooper pair transport.
I see. So there are measures taken to just completely suppress.
But again, you can never be 100% free of quasi-particles, but as long as they happen, the simple thing they do is that they introduce a channel for normal transport, which means resistive transport. So it introduces some kind of a dissipation. It can have other effects in other cases where it behaves like an extra charge because you have an extra quasi-particle sitting around, and that can cause a shift in your qubit properties as well.
And that would come as a resistor, either, I don't know, whether
That's
in
one
parallel or
model.
series.
The resistor as one of the models, yes, that would. But if there are if the quasi-particles are hopping on and off, at a very slow rate, then I can't just put a resistor there. It's more complicated than that. It's a dynamical process.
Okay.
Yes. Oh, so I have not said anything about dephasing or decoherence at this point because I have not said how these quantities can change in time, right? So the relaxation process comes when this object is not actually what you're implementing. The capacitor has some resistance across it because of dissipation in the dielectric. As we were saying, the Josephson junction could have a resistor across it because of quasi-particle transport. Same with the linear inductor. Plus, you can have other mechanisms which is causing this Lj to fluctuate slowly in time. None of that is represented in this simple circuit. Here, everything is considered ideal. Decoherence has not been considered at all. But when we write down the Hamiltonian, anyway, we never consider, typically don't consider when we are interested in looking at the energy spectrum and how the level structure looks like, right? Dissipation sort of comes in at a later stage. Okay, so just to orient you, these two junctions, see, they are connected by this loop. They're actually in parallel. So I could have just made one junction and completed the circuit like that. The two junction just means that I can apply a magnetic flux here and tune the Josephson inductance, or sometimes we refer to as Josephson energy. It's just allowing for tuning. So it's a junction, there is some capacitance, and there is a voltage source, and that's it. That's the circuit. The capacitance shunting the Josephson junction, which we were considering for the transmon. In this case, there is no separate capacitor. It's the intrinsic capacitance. That's why this is drawn with a square box around it. So the Josephson capacitance is the only capacitance in the picture, which means the capacitance is small. That's the regime in which this so-called charge qubit or Cooper pair box operates. And this was experiments done in the late 90s in France and also in Japan. So in these kind of qubits, this point here, this intersection of the Josephson junction and this capacitor, the capacitor is basically just a gap, right, between these two electrodes. This is referred to as an island. It's an island because it's a localized piece of metal, which is sort of disconnected from all sides. Here it's disconnected by a capacitive gap. Here it is disconnected by a tunnel junction. So there's an energy cost for, say, a charge here to jump across from either side. So this was sort of the picture of qubits those days, that you have an island which is localized, and there is an energy cost to add charges to this. So you can start imagining why something could be quantized here. Like you have, you put a charge, there's an energy cost. You have to put another charge, there's energy cost. And if this energy cost is higher than thermal energy, then you have quantized charges on these islands. So if you now look at the Hamiltonian for this, you can write it in this charge basis. So typically these are parameterized in terms of these two energy scales, just called EC, or the charging energy, and EJ, or the Josephson energy. So the charging energy is really just the energy required to put a charge of 2E across this capacitor, but this capacitor is now consisting of three components. This is the gate capacitance, which is the difference between this island and this voltage source here, and also the capacitances of the two junctions. This is sort of the effective capacitance shunting this island. So that's the capacitance you have to charge up with the charge of 2E. So it's basically Q square over 2C, or 2E square over 2C sum, the sum of all these capacitances. The Josephson energy is essentially given by H bar over 2E I naught into 2. And in terms of this, you can write down the Hamiltonian in the basis of charge state. So this N is the number of excess Cooper pairs you have on this island. And that depends, it's scaled by EC, because each time you add a charge, you need this amount of energy. But there is now this other factor, which is Ng. I'll come to that in a second. And then this is the Josephson term, which basically plays a role when the charge changes number, because it has tunneled in and out of this Josephson junction on the other side. So it connects two different charge states, and it gives you this energy term EJ cosine delta, where this delta is actually related to the phase difference which is developed across this junction when you have a flux over here. This Ng is essentially the effective charge on this island induced by this voltage source. So it's actually this voltage scaled by this capacitance. So it's actually CG U over E, or 2E, depending on the conventions. I think here the convention is 2E. So that actually affects the energy dynamics of this island. So for certain values of gate charges, the tunneling can become easier, and for other gate voltages, it can be blockaded. Right? So if you now look at the spectrum of this system, it's plotted as energy levels as a function of this gate charge, Ng CGU over 2E. So this, in this plot, it's normalized in terms of one electron. It really doesn't matter, it just changes the axis here. I want you to first look at the dashed lines here. You see these dashed lines are like parabolas. Why? Because E square, charge square over, is basically goes as a parabola. The energy increases quadratically, but there are these points where two different parabolas cross each other. These are the two parabolas corresponding to two different discrete number of charges on the island. So you can say that this is excess charge 0, this is excess charge 1 Cooper pair. But these points where the energy levels become degenerate, the Josephson tunneling element here, it breaks that degeneracy and gives you this splitting here. So these levels have now been distorted, and there's one level which is pushed up, and there is one level which is pushed down. So here it's an extreme version of that, because this was created for a plot where EJ was quite large. But you can now see that the lowest two energy levels has this kind of spectrum. And as a function of gate charge, these levels actually change. So this charge qubit, the transition frequency of the ground to excited state is charge dependent. Right? This was a very important feature of the experiments at that time. So at this point, I want you to show you this tool, which is quite nice. And I'm sure many of you have used this particular tool. This is a Python package. I think it comes from the group of Jens Koch in Chicago, where you can just put in the type of qubit you want, set the parameters, and it solves all the basic things here. Okay, so you download the package and you just import this, and you just run this. It's really quite fascinating. I'd seen my students use it, and so last night I downloaded this and set it up. So here I've set up the parameters for this charge qubit. So here you can see this a little bit more clearly. So you can see this outline of these parabolas here. And then there's a gap opening up, which is basically related to this Josephson tunneling. And I can now show you if I change the Josephson energy here, the gap opens up. And if I make it smaller, the gap becomes smaller. So as EJ becomes small compared to EC, this becomes more and more in the charging regime, where the quantum states can be really thought of as discrete charge states, but not near this point. The qubits which were done in the early days, they used to work anywhere here, but then people moved to this particular point for a reason. And that reason is that at that particular point, let me now just zoom into a few levels here. If you operate exactly here, which is Ng equal to half, so here it's parameterized in terms of Cooper pair. So this is 1 electron worth of charge set by a DC gate voltage. Here, the difference between these two frequencies is first order insensitive to charge, right? Because there's a derivative, the derivative goes to 0. So you get some protection from charge noise. So for those maybe who have never heard this, turns out that when you make things on substrates, there are always charges jiggling around in your neighborhood. And these act like a noisy gate voltage on your device. And turns out there's nothing we can do about it. So people saw this, they knew about this, they saw that this was very bad. The first thing that was done was to move to these so-called special points, which are called sweet spots, where they become first order insensitive, and you can directly see that your decoherence times improves, especially the dephasing time improves significantly at this particular point. But other things also change. The matrix elements between these elements could change, so that can affect the relaxation time. If I remember correctly, the matrix element, I think, is the strongest here. So in terms of relaxation, this is the worst point, but in terms of dephasing, it's the best point. But it could be small enough that you can still work with that. So this is really a nice tool. And if you now sort of keep increasing this, you can sort of see, if I add some more levels here, let me go to very small EC and very large EJ. You can see that as I increase EJ and reduce EC, these levels start to flatten out, right? So they become less and less charges. So this is actually the evolution from the Cooper pair box, which was a charge qubit, was sensitive to charge noise, to the transmon qubit, which is insensitive to charge noise. Okay. So the transmon qubit is actually here. That's a typical transmon. It's flat as a function of gate charge. So you just don't put a DC voltage anymore. You don't care where this axis is, because you're no longer sensitive. Of course, there is a small effect remaining, but it turns out that it's exponentially suppressed. And the price you pay is that now this looks like a harmonic ladder. You have some nonlinearity, so you compromise anharmonicity, but for exponentially reduction in sensitivity to charge. Okay. So I recommend this playing around with this. It really gives you a nice feel, because you can, and it's quite fast in terms of how it computes. You can also see wave functions, right? And what does this remind you of? These are your harmonic oscillator wave functions of the transform. So the ground state is just a Gaussian. The first excited state has one node, remembering your first year quantum mechanics, and so on and so forth. So you can also see that as you change the parameters, how the shape of these wave functions change. And there are many other things. It also computes matrix elements and things like that. Yeah. Yes, always. But non-ideality in what sense? Dissipation? See, dissipation has no role in the Hamiltonian prescription and energy spectrum, right? You can have non-idealities in the sense that, so if I remember correctly, this basic version has some standard defaults, but if you go into the package, you can actually construct any circuit and it will solve the Hamiltonian and give you the energy spectrum. There are other packages like this as well. So you can have, for example, what happens if these two junctions are not exactly identical. So they make small changes. So there is this thing called tunable transmon here. which has this asymmetry parameter, which is the asymmetry between the two junctions, and also how much flux bias you are applying. So you can see that it actually gives you the circuit here, it gives you the Hamiltonian, it gives a picture from literature. What I found really fascinating was that they have given you literature parameters. So you can say, hey, I want to see the Hamiltonian for what was the device that was used in this paper, and you can select that. So they have chosen a few standard references. So it's really quite well thought of. Okay, so now moving on from the Cooper pair box. So as I said, this was sensitive to charge noise, and there was dephasing. So the first sort of improvement which happened was to go and operate at these points where you are first order insensitive to charge. And that led to sort of, I would say, the first major improvement in coherence in qubits in 2002 from Saclay, where they made this thing called a contronium circuit. Okay? Again, looks very complicated, but it is the same circuit. It's the Cooper pair box. So you see there are these two junctions in a loop. The only difference is that this loop now has another junction in it. It's a much bigger junction, which means critical current is large, so the inductance is small. So if you think electrically, the dominant inductance of this circuit is actually still from the small junctions, which are the relevant junctions for the. Oh, there's a. Oh, I see. That's not in my point. Okay, I'll answer that question in just a bit. So, and I'll explain why that is needed here. But otherwise, it's just a Cooper pair box. So you see here is the capacitor to the gate voltage here, which has a DC part and an AC part for doing the excitations. And the parameters EJ and EC are chosen so that the charge, the variation of the energy levels with charge is not very strong. And then you apply a DC voltage here to sit exactly at that point. Okay. And so the point was to operate at this sweet spot where you are insensitive to charge noise to first order. But the problem here is that there is no charge signal at that sweet spot. And this I didn't really mention before, but the early qubits, the measurement of what the quantum state was based on some kind of a single electron transistor, which is sensitive to charge. Because the two states have slightly different charges on the island, you could detect that. But at this point, which is basically here, these are symmetric and antisymmetric superpositions of the 0 start state and 1 start state. So their average charge is the same. So there's no charge signal to measure. So then how do you detect it? So that was a major innovation in this experiment, is that they introduced this other axis here by introducing Josephson junction, and you measure along the phase axis, and that gave you a way to measure this while still operating at the sweet spot. And this was the first time you saw these Ramsey fringes, which are shown here. This is the Ramsey experiment I showed you, and I think the decay constant here was around 200 nanoseconds, which was, I think, already more than an order of magnitude compared to the conventional charged qubits at that time, because this was published in Science, and it was a big deal at that time. I believe I've seen, so my advisor, thesis advisor, Michel Devereux, was part of this experimental team, and I think he has a printed copy of this Ramsey fringes signed by Norman Ramsey, confirming that this is indeed Ramsey fringes experiment in his office. So just a personal note here, this was actually the starting point of my PhD career, and I worked on changing this measurement scheme which used DC techniques to AC techniques by essentially treating this large Josephson junction plus this capacitance as a nonlinear oscillator, and using the nonlinear bifurcation of driven states here as a way of detecting the quantum state. So basically the nonlinear oscillator would either be in one of its metastable states, depending on whether the qubit was in the ground state. And this was again further developed in a series of papers, and both at Yale and also at Saclay, in the previous group of Michel Devereux. So you went from charge sensitive devices to charge protected operating points, and then you went to your transmon, where you essentially chose the value of EJ and EC in such a way that you are now completely insensitive to charge. So here's a sequence of plots from this really seminal paper from Jens Koch when he was at Yale. And they show how the spectrum evolves for different value of the ratio of EJ over EC, to going from highly varying in charge to completely insensitive to charge. And this plot actually shows you how the charge dispersion, so the charge dispersion is defined as what is the difference in frequency between 0 charge and 1 electron charge. So because that's the maximum variation you can get, plotted as a function of EJ over EC, and this is a log scale. And this was really the thing which made this work, is that the charge dispersion suppressed exponentially, whereas the anharmonicity sort of only went maybe polynomially. So you didn't become completely linear in order to lose the charge sensitivity. And that was sort of the sweet spot of charging regime, typically around 80 to 100 or so. That's sort of the ratio one uses. And then you can adjust the other parameters to get the frequency in the range you want, which was typically, as I said, in the 4 to 8 gigahertz band. Okay, so again, trade anharmonicity for exponentially reduced charge dispersion. The anharmonicity is good enough for fast operation. Why do I say that? If this was very close to each other, then a fast pulse on a 0 to 1 transition will have a finite bandwidth, and it will start pushing population from 1 to 2. This is called leakage out of the computational subspace, and that can still be suppressed. So the difference between these levels sort of sets a limit on how fast a pulse you can do. But this is, as I said, this number is usually around 300 megahertz, so you can make nanosecond scale pulses, which is good enough for these experiments. And again, quantum state measurement was still possible, right? So you went from this charge sensitive device, which had a difference in the charge between the states and using a charge sensor to detect, to something which goes to a sweet spot with no charge signal, but you use an orthogonal axis to measure. I remember because this happened next door to my lab in the group of Rob Sholkoff. And initially, and we were so used to thinking in this other way, this sounded that this cannot work. It's like here you have one oscillator and you're measuring another oscillator. How can the two affect each other? Everything just looks too linear. But as very nicely explained in this paper, turns out that there is still a sufficient signal to be measured without compromising any of these properties. Right? And finally, let's see, how much time do I have? I think maybe I can start with this one in the next lecture. I will move on to this last slide here to sort of just comment on this, the measurement part. So we have seen this picture here. So this is sort of equivalent to an atom inside a Fabry-Perot cavity. And the Hamiltonian of this looks like this. So here you have written the qubit as a spin half particle with just 2 levels. And you've written your oscillator as a harmonic oscillator variable. And then this is the coupling form. This is what is called as exchange coupling or Rabi coupling, where essentially you're killing one excitation in the qubit and creating one excitation in the oscillator and vice versa. That's sort of the starting point of this Hamiltonian. But then you do a dispersive approximation where the frequency of these 2 oscillators is far detuned with respect to the coupling strength. And then when you basically do perturbation theory and find the leading order terms, you get an expression like this. So you have your qubit, but now your cavity term has a qubit state dependent term in it, right? And it's this part which basically tells you that the omega resonance at state 0 is different from the omega resonance at state 1. And you saw these plots yesterday as well. And that gives rise to the ability to do measurement. And it turns out that because the measurement Hamiltonian, which is sort of this interaction term, commutes with the qubit, this implements the textbook quantum measurement, which we learn about. And it's often referred to as quantum non-demolition, which often creates a lot of confusion. But what it means is that what we learn as this measurement postulate, that if you have a superposition state and you make a measurement, the measurement gives you one of the eigenvalues of the measurement operator. And post-measurement, the state of the system is the eigenstate corresponding to that eigenvalue. This is the textbook ideal quantum measurement, and this Hamiltonian allows you to implement that. Okay. So in the next lecture, I will finish up with the fluxonium, and then I will spend a little bit more time on this measurement-related things and talk about some experiments. and other kinds of science experiments people have done using these superconducting qubits as well. Okay, I'll stop there and take some questions. Maybe I'll start with that, addressing that question. So I think the question was that, why do you need superconductors? It looks like I've just created some kind of quantum dot. Yes, but as I mentioned in the previous lecture, the superconductivity basically allows you to minimize the dissipative processes in the system, giving rise to coherence times. There are, of course, different regimes where quantum dots are used, and especially at high magnetic fields, but that's a completely different regime of operation. So here, we cannot think of these as quantum dots. Yeah.
One comment about the picture you showed about the intersecting parabolas,
yeah,
which involve a 2E transfer.
What about this?
So just to show, to demonstrate that this is a not a non-trivial, a quick story.
Yes.
Back in 1984, I was a postdoc in Santa Barbara, and Eshen Ben Jacob and I, and independently Licharev, wrote papers about single particle or two particle oscillations. And almost the vast majority of the community thought this was complete garbage, including people like Bob Schrieffer, Tony Leggett, others. And the argument, there were many arguments. One argument was, look, Yuval, the smallest current possible involves 10 to the 9 electrons per second. So are you telling us that 1 electron can be observed? And a few years later, it was clear that that was correct. So it's highly non-trivial, I think.
Oh, yes. And a side fact is that, see, these parabolas here are shifted by 2E. If you don't do things properly, and I think this happened a lot in the early days experiment, you will see parabolas in between the two, which are the single charge states. And they often poison this. And maybe to add to what Yuval said, I mean, I remember facing these kind of criticisms, I mean, not myself, but the sort of the community at that time, where everything was looked at with suspicion. It's like, this is not possible. You see some effect, oh, that is some heating because you're applying some microwave signals, something is heating up. I remember I used to find it very funny. Anything can be explained by something in heating. It really took, for example, a lot of people sold oscillations, right, which looked like Rabi, but that was not enough. You had to show that those oscillations scale linearly in frequency with amplitude. Only then you can say that this is driven two-level physics. And I think some very early experiments in some platforms had not been able to do that for various reasons. So there was always a suspicion. I mean, even very recently, I've had questions doubting the existence of this phenomena even now. So, it's, I mean, I think it's really got to do with the kind of thinking you have come from the field you're working. It sometimes becomes very difficult. And, in general, solid state systems are just considered so dirty and uncontrolled. And they are, I mean, there are lots of problems, but if you start understanding every aspect of them and slowly fix them, then you can actually get all these quantum coherent. Now nobody even, thinks twice about any quantum effects in these kind of systems. Okay, any more questions?
So,
yeah.
So I have a general question. So if you move from the qubit architecture to Q-treat architecture, how does the complexity changes?
Qubit to Q-treat. So it really depends on what you're trying to do. So the transmon actually is a qubit. It has many levels, and many people have done experiments using more than 2 levels as well. Something we had also started looking at some point of time. There are some advantages in certain protocols. There are some error correction protocols which become more efficient in terms of the resources you require. It's really, again, at some level boils down to this question of why did we stick to binary system for digital communication, right? There are some technological reasons, some fundamental reasons. A, binary is sufficient to do anything. So similarly for quantum computing, 2 levels are sufficient to do everything. As we progress towards the ideal quantum computer, we will probably see some things involving multiple levels, which may allow you to do a certain experiment today with the limitations we have and do it better than, say, a qubit topology. But fundamentally, there is no reason you can do it as well. A side point here is that there is a whole another branch of doing qubits, which doesn't use just these individual levels. It actually uses many levels of a harmonic oscillator, but different superpositions of those. This is basically what's called the bosonic codes and cat state qubits. And I think Serge might talk about them, maybe, no? But he works on those, so you can talk to him. And again, when it came about, everybody who was trained in this field, it's like, wait a second, we just spent 10 years giving a lecture that harmonic oscillator is not very good for a qubit. And now suddenly you're saying you can make qubits out of harmonic oscillator. And the advantage there is that the Hilbert space is so much bigger, it allows you to do certain things very naturally, and error correction is very natural in those systems. So that's another area.
Okay, so I have another follow-up question.
Yeah.
So
maybe let's take this one, I'll come back to you.
So my question is, when you discussed about T1 noise, you said that you average over many trajectories.
Yeah.
So my question is that in an experiment, what is the probability of generating trajectories with same sequences many times? So.
Oh, so see that. So she's asking what is the probability in an experiment to generate the same trajectory over and over again? I mean, it's very small because the trajectories are random. So what you can ensure is that the initial condition and the experimental, whatever you're applying for evolution or measurement, is kept identical, but the actual evolution will be random. But there are experiments which have been done where they have chosen a subset of trajectories which are closest to one trajectory you have chosen and created like an average, a conditional average of those things. So these kind of experiments have been done. But the trajectory by definition is a random process. I cannot predict it.
To do an ensemble average, you have to have that same sequences many times, right?
Oh, only the initial condition and the experimental condition. The ensemble average comes, it's not many exponentials being averaged to get better signal to noise ratio, right? So if you think in terms of quantum jumps, it's various types of, so it's various quantum jumps, each one of them happening at different times. And then when you average all of this, you get an exponential curve.
So that is what I'm saying, like the jumps are occurring at different times. So those different times would be like, would signify one of the sequences. So these are like different, if the jump is occurring at different time, these are like different sequences then.
No, same sequence repeated over and over again. So the way you can think about it, if you want to think it sort of classically and say that there is some noisy signal which is giving rise to this jump evolution, then each time you do the experiment, it's a different noisy signal from the environment, which is giving rise to a different trajectory and a different jump time. So you can only maintain the experimental condition. The trajectory itself would be random every time, but the average trajectory will show exponential decay for this kind of a process. Okay. Yes.
But there is also such a thing as gate noise.
What noise?
Gate noise.
Gate noise.
So the pulses that you showed, which implement your gates, now they may not be exact and so on. Do we today also have experiments like the ECHO or the T1, T2 experiments that you showed, which can give us a good handle on a model of the gate noise?
So just to elaborate on the question, what she's talking about is that, let's say I calibrated and I found a particular time here, which gives me the pi/2 operation. Every time I do this experiment, because of technical issues in my electronics, I'm not always going to send the same pulse. It's going to be a very small difference depending on how well you have calibrated and how good your system is. So that can appear as a noise in your system, and you can actually calculate the effect of that by assuming a perfect pulse, but some additional noise. Am I explaining this correctly?
That's right. Yeah.
Right. So of course, people have come up with various protocols to analyze this. I have not worked on this particular type of experiments that much, but things like randomized benchmarking allow you to give some overall number from these things and say that, okay, I can assign some kind of a gate fidelity to my operation, right? And essentially it does it by doing a whole sequence of random operations which always bring you back to the same state. And then you see how well you reach that state and look at deviations from that. But this is, this is definitely possible. I don't know too much about this off the top of my head.
This is more heuristics that we have now in some sense. We don't have more, theoretical understanding of this, how the pulse shape or the pulse deviation from the ideal pulse.
Well, you can make, knowing your experimental setup, you can make reasonable models for the kind of things that can happen. One is just simple. You can say there's some Gaussian distribution in my pulse length or my pulse amplitude, and that will just move you up and down this point. And you can factor that and see how that affects your overall operation. But typically what happens is that in a real experiment, you do this, you have some measure which says that, okay, my pulse is now too far from what I wanted. So you go back and recalibrate and fix it and try to ensure that it's not affecting your problem. And Serge, maybe correct if I'm wrong, but I think for most high-end, like top of the line experiments, the limitation is not due to these kind of problems, it's still coherence. Right? That's starting to change again because now the coherence has become quite high, and then you again, so then you will improve your electronics, and it's sort of, you'll keep going back and forth.
Thanks.
Assuming you have done everything, again, these calibrations can be very tricky, and some people can't do it right, and you can.
One sees that actually it's the gate noise that today seems to kill you more than even decoherence.
It's possible, yeah. Maybe come back here.
You said that the dephasing noise or the charge noise is one of the noise models. So
Yes.
that has been taken care in the transmon qubits.
Up to a certain
level.
yeah.
So apart from that, what else noise model do you face in that architecture?
So in the transmon, there is still dephasing happens, which basically tells you that it's not only charge noise which can cause dephasing. And these are due to slowly fluctuating two-level systems in various parts of the circuit. Could be in the barrier of the insulating barrier of the Josephson junction. It could be in the thin layer of oxide which covers all your metal surfaces. So imagine that you have a parallel plate capacitor, right? And there is some dielectric medium, but inside that medium there is some atom which is shifting between two positions over some small time scale. So these kind of things we refer to as two-level systems because they have two configurations, and that can happen due to defects in the crystal structure or the actual structure of atoms. And that change of that position affects the dielectric constant of the capacitor because now the electric fields are slightly different in the two configurations. And capacitance translates to a frequency change, and that frequency change translates to dephasing noise, right? So this is an example of that. You can still have quasi-particles coming in and out of your circuit, which can give rise to frequency fluctuations depending on the particular circuit. So all these different qubits are affected by these different processes by differing amounts. So one has to, and there are experiments which allow you to characterize which of the noises you seem to be more dominated. And then over the years, people have tried to fix these issues by better shielding, using different materials to reduce the dielectric losses in two-level systems, and so on and so forth. That sort of, at least for now, is one of the major